Yeah, thank you very much, Sebastian, for inviting me and introducing me. Good evening, everybody. Thanks for coming along. It's about rankings and recommendations. League of Geeks in Passau. It's the very first time here. I tried to attend a former meeting, but didn't make it, so I don't know what expects me here. So please be very nice to me. My name is Stefan Fischerländer. I'm co-founder of Gipfelstolz, a digital consultancy agency, once based in Passau, now completely remote. I'm doing, as Sebastian told you, SEO consulting for about 20 years now. And yeah, I'm really old, getting older every year. But as you've heard, I studied physics, so this marketing discipline, SEO, has a very strong technical side. And from this technical side, I came, and it's what I'm doing and what I'm fascinated by SEO. And there's another reason why I think I can talk about ranking algorithms. About 15 years ago, I developed a search engine, Neomo, did a startup with 3 yellow pages, publishers in Germany, and this was then based on 200 million monthly pages, was running on 40 servers, and there was no nudge or Lucene or something at that time, so we've written everything from scratch. It worked rather good, but the yellow pages publishers were the wrong partners for us. That meant they had problems with Deutsche Telekom, and partnering with Deutsche Telekom is very difficult. So in 2007 we ended this project. But in the meantime, I learned a lot besides my SEO job about ranking algorithms. I read a really big list of research papers about it, did a lot of experiments. We had an index with 200 million pages, so we could experiment a lot. And this is what helps you to learn and to understand what search engine algorithms are about. So the first part and the largest part will be about rankings and ranking algorithms and how you can reverse engineer them. At first, I want to give you a little bit a glimpse back in history, how search engines once worked. In the 1990s, in the pre-Google area, it was all about exploring the HTML content of pages. You were looking at, is the keyword that's been queried for in the title, is it in the body tag, how often is it there, is it in headlines, what's the keyword density, is it in meta description, meta keywords, etc. And how did we re-engineer these engines then? Oh, we were doing a lot of experiments, because that was easy. It was just about the HTML content. You could change it from one day to another. Some search engines were rather fast in indexing it. One search engine from Germany, Fireball. Does anyone remember? Yes. Okay, 1, 2, 3. These are the older ones in here. Fireball was very fast in indexing. So if you were changing your HTML and we're submitting it for re-indexing after midnight, it got the timestamp from the new day, and the new day meant it had a large boost. So it was rather easy to find how Fireball was indexing, what the parameters were, and so you could find out exactly how the search engines were working. And of course, we read a lot of research papers to understand how that was working. In the 2000s, or you could say Google Mark I, there was Google. And Google was special because it was the first search engine that really paid attention to links. And of course, you've heard of the PageRank algorithm. And I recently read that PageRank algorithm is the key factor of Google, but that is nonsense. The key factor was that Google was paying attention to the anchor text on other sites and the link to the sites. And this anchor text was accompanied to the link to the site. So an example that's just working till today. If you're looking for the word here, on position 3, you get Adobe Acrobat Reader download page. Why? Yeah, a lot of pages have PDFs to download, and they said, here clicking to download Adobe Acrobat Reader. And now Google came and said, okay, there are thousands or tens of thousands of pages linking to that page with the link text here clicking. So this must be a really good hit for here clicking. And this is how Google worked. And this is how it was easy to re-engineer Google One, because you could see such effects, and there was some kind of errors, or so-called errors. One example is miserable failure. Does anybody remember what that was in connection with Google? It was about 2000. It was the presidency campaign in the US, and when you were Googling for miserable failure, position number 1 was an official website of George W. Bush. Google then said, oh, I'm sorry, this was an error. But it wasn't an error. The situation was that there were several people who were not very fond of George W. Bush and linked to his official page with the text miserable failure. And if you clicked on miserable failure, you came to his official page. So Google learned, oh, the text miserable failure is linked with George W. Bush, and so it was number 1 because nobody else was optimizing for miserable failure. And this is working till today. Google does a lot to avoid spamming it. It's sometimes called Google bombing, but at the core it's still working, and it's still one of the most effective SEO tactics. And then in the 2010s, or Google Mark II, there came another very important signal, and these were the signals that came from users when using and interacting with the search engines. For example, you're looking in Google for something, you're clicking on number 1, but the page you find is not very good, it looks rather strange. Then you click back and click on number 2, and there you stay on number 2. This is a signal for Google to say, oh, number 1 is not really good for this query. So if this are doing a lot of people, number 1 will disappear from its spot. And a lot of other similar things. These are a lot more difficult to re-engineer. It means to read a lot of patents. It also means a lot of guessing and doing some correlation work. And correlation work is, I'd say, the most important thing in reverse engineering search engines. This is a slide from Searchmetrics, one of the search tool providers, and they did a correlation and correlated the usage of microdata integrations with the top 10 rankings in different niches. And I found for recipes, nearly all of the top ranking pages have microdata integrated. So you could think, oh, I have to integrate microdata if I have a recipe website. But it has not to be true. Because, yeah?
What does microdata mean in this context?
It's an integration in your HTML code, and Google uses it to show the star ratings, for example, if there are reviews or events. It shows the time in the description of the search result. And microdata is one way to transmit this information to Google. So you could think, oh, I have to integrate those microdata annotations in my website when I'm doing a recipe website. But of course, there's a special microdata dedicated to recipes. Everyone who has a recipe website integrates it, so it's no distinction. So this very high value just means, hey, there are a lot of recipe sites. They're doing good online marketing. When you're doing good online marketing, you get top 10 rankings, but you also integrate the microdata. So there's no causation that if you integrate microdata that you get better rankings. So, and you have, as I said already, to read a lot of patents. This is a very new one. It's very interesting because Google employee in February said, we don't do things like dwell time, we don't do things like click-through rate on search engine result pages and such crap, was his words. And now, 4 weeks later, there's a new patent that describes how Google does click-through rates and dwell time and so on. But it's getting more and more difficult because there are a lot of hidden parameters. User signals means you don't know a lot of data anymore. Formerly, you could look at the HTML code. You could crawl the web by yourself and get a lot of links, or there are several tools like Searchmetrics or Systrix that do that for you. But the usage signals, you can get some of them via analytics or Search Console for your own page, but not for other pages. So that's really, really difficult. So now to reverse engineering. I have some slides for Google. Google is really well known as a search engine by the SEOs because it's intensive reverse engineering going on for about 2 decades. There are a lot of tools with a lot of data. Many SEOs are reading patents and research papers and doing a lot of experiments. Some of them not deliberately, but because they make some errors where we can learn a lot of. But there's also going a lot of correlation exercises on. One of them is now 10 years old. I showed it on a conference 10 years ago. And these are some correlation charts I did back then. On the x-axis are the positions in Google from 1 to 100. On the y-axis is the value. Here, for example, is the keyword in the title for about 1,000 keywords. On the left, the blue one is long-tail keywords, keywords that are very seldomly searched. And on the right are blockbuster keywords like Facebook or weather or soccer or something like that. And so you can see, in the blockbuster world, you have to have the keyword in the title. Otherwise, you don't have a chance to get a top position. Long tail, there's a strong correlation to see between better rankings and the title in the keyword. So we've learned the keyword in the title seems to be important. Same, you can see keyword density in the title. Keyword density meaning when the title is 10 words long and your keyword consists of 2 words, then you have 2 from 10 is 20%. Or keywords in the H1 headline, or a very strong correlation, keywords in the domain name. And this is another thing you can learn from these correlations. Of course, you can't reach number 1 just by buying a domain name with the keyword in it. What happens here is that there are a lot of domains using a keyword with a domain in it, and they are linked to. And if anyone links to our website gipfelstolz.de, what are they writing in the link text? Gipfelstolz or gipfelstolz.de. And if anyone links to italien.de, they write in the link text, in the anchor text, Italien or italien.de. And so if you have a domain with the keyword in the domain name, then you get a lot of links with the keyword you want to optimize for. And this gives this strong correlation, but of course you cannot derive that you just have to buy a domain name with the keyword in it. So this was a few back for about 10 years. So what about personalization? A lot of people say, oh, personalization is so big, all those reverse engineering isn't helpful anymore. but I think it's extremely overestimated. I've done a lot of experiments, and I always get the same results, no matter if I'm logged in or not, or what searches I've done just before. So in the core, Google always brings the same results. So much for Google. I want to focus on YouTube, because for YouTube we can learn, or we can demonstrate the reverse engineering process a lot better. Yep?
Sorry, if you're coming to that later, but I didn't really get why we're doing it. Like, why are we reverse engineering? So what's the stake?
Oh, as a SEO, I want to know what I have to do to get on #1 for my keyword.
It's like I'm a company and I want to get on #1 on
Yep.
Google, so that's the reverse engineering.
That's the most important reason, of course.
Yeah. So it's
And as a-
understanding how the search engines work.
And as a technical person, I'm just interested in how they work.
Yeah.
And what are they focusing on. That's interesting for me. Yep.
But to add one factor, I think has big impact on Google search results is your geolocation.
Yeah, of course.
I think that's pretty hard to reverse engineer, maybe with lots of VPNs or so. I don't know.
Yeah, you can change the location parameter in Google on the URL. So you can simulate it a little bit. But you're right, it's hard to reverse engineer. And for different queries, it can have an enormous effect. Sometimes it's different by city, sometimes different by Bundesland, etc. But this is, of course, one problem, yeah.
Yeah, because Google sells the Google AdWords service, especially for local search results.
Yeah. So this is just for the broad queries, for the general queries that are not affected by local effects. But there are a lot of queries affected by local effects. All the shopping or product searches are affected by shopping. But it's some kind of meta search engine going on. The normal results and the local or shopping results faded in, and two of them, and so on. So why YouTube? Because for all those correlation work, you need a lot of data. And Google provides a data API. That's good. The problem is it's rather restricted. For this talk, I was analyzing 2,500 videos from about 1,400 channels. And I tried to show this in a Jupyter Studio in Python. Yeah. So you're not seeing it, I'm seeing it. I hope we can change this. So we have a lot of modules I'm using later on, and some configuration going on. And I have several methods defined to access the API. So I try to fetch the videos for Bayern München. And they are stored in the array video IDs. And those are video IDs from YouTube for the query for Bayern München. This I did for 50 queries, fetched the 50 best ranking videos, and fetched for all of them the video details. And then you could get the details from the API, the description, there's a title, the snippet, thumbnails and so on, a lot of tags, and some statistics like how many views got this video, how many likes and so on. So I've stored it because the API is a little bit slow and you have to use several API keys to get all the data I need. So I won't do it again. It's stored in several JSON files. I read and create a data frame for this. The data frame, just a table, looks something like this. There are the comments, the YouTube ID, the likes it got, when was it published, the query or the file name the query was stored in, the rank the video was positioned, and the tags. So now try to get some correlations to understand what's happening here. The first what I tried was just to do a scatter plot. On the x-axis, the position, the rank from 1 to 50, and on the y-axis, the number of views. And you see there are several videos with a lot of views. It's about 1 billion here on the top. But you can't see anything useful because most of the videos have just about 1 million or less views. And those are the ones that are hidden here in the blue dots. So, and if you do a correlation coefficient, you get a value that's rather low, about 0.08. That's not very, very strongly correlated. So I tried to do the same with logarithmic. On the y-axis, not the views, but the logarithm of the views. Now the regression line looks a little bit better, and the regression now is by 0.19, but it's not really good. So this doesn't give us a lot of useful correlations. So what it's meaningful to do, to create the mean data for every position. I'm not looking at the distribution for number 1 and the distribution for number 2, but at the mean for all videos on number 1, or for number 2 and so on. So generating new data frames just for position and the average view number. And if I'm plotting this, this is a little bit more what we expect. Once again, x-axis are the positions from 1 to 50, y-axis the number of views. And you see the views, the videos with more views are better ranked than the ones with less views. Besides number 1, 2, or 3, they get rather, the top position with rather few views. That's something we'll look on later. The regression for this is a lot better, 0.6, so it's really correlated. So much to the views. Now to the likes. The same thing, scatter plot, nearly not correlated. So I'm doing it again with the mean. Oh, nearly the same picture. Strongly correlated, likes to position, beside number 1 and number 2. There are some kind of outliers. The regression, the coefficient for this is about 0.67, rather good correlated. Then we're looking at the comments, doing the same very fast again. You see the same pattern, strongly correlated, besides number 1 and number 2. Correlation value about 0.7. So why could this be that number 1 and number 2 are so different from all the other rankings? One idea I had was, oh, let's look at the age. So I've made a little function that's calculating the age of the videos in days. I'm plotting it again. Scatter plot shows nothing. The correlation is nearly at 0. So again, the mean values. And then you see top 2, top 3 videos are rather new. And position 10 and lower are not correlated to the age. So it seems there's some kind of boost for newer videos, and that's not really surprising because YouTube wants to avoid that there's always the same video in front of it, just because it has a lot of views and a lot of likes. So this is really meaningful and reasonable for YouTube to do. Again, correlation value about 0.35. Not as good as likes, but not that bad. So, but we have just been looking at the videos, but every video is in a YouTube channel. So channels could have some influence too. So I was fetching the channel data as well. So I now have the channel ID to every video. I'm fetching the channel details from the API, doing this as an example for a single channel. You'll see the infos you get. It's magenta sport, a description, and down here some statistics, the view count of the channel, the subscriber count of the channel, and something like that. So I can fetch this again from the API. I've done that, loading it, about 1,400 channels. And in my variable channels, there's now for every channel the statistics from the API. So building a new data frame. We have now for every video the rank it was positioned on, the title of the video, accompanied by the number of videos in the channel and the number of views of the channel this video is in. Now I'll do my regression tests again, scatter plot and linear regression, bad as it has been all the time. So I have to calculate the mean again. And I'm seeing that the subscriber numbers for the YouTube, for the videos, is not correlated at position 10 or lower, but the best ones are strongly correlated with the number of views. This isn't also not surprising, because if you have a channel with a lot of subscribers, your videos will get a lot of views just because you have a lot of subscribers. So please don't show all this analysis to your statistics teachers. They will kill you or kill me. So it's rather casual statistics what we are doing here. But think of all the hidden parameters. It doesn't make sense to do a lot of really correct statistics, because we know there are a lot of parameters we don't know. We just can't find some of them and get some understanding. So the value here about 0.34, not that bad. So channel views, the same as with the subscriber number. Of course, a lot of subscribers means a lot of views, not very surprising. The number of videos in a channel, how large a channel is, seems not to be correlated at all. The value is just 0.07, really low number. And of course, there's a lot of correlation between subscribers and videos. I've calculated it as well, with a correlation value of 0.5, but that's hardly surprising. Till now, we've just been looking at the subscriber numbers, view numbers, etc. But every video has a title and has tags in it. So I've calculated a text score for the title and for the tags. The text score gives you 4 points if you have an exact match, and 1 additional point for every word from the query that's in the in the text, in the title or in the tag. For example, the query große Aber gets 6 points for the title skiing große Aber GoPro. If it was the other way around, it just gets 2 points because you don't have an exact match, because große Aber is not in the title anymore. You just get 1 point for große and 1 point for Aber. Abilities to calculate such a text score. This is just one very basic one to get the idea. I'm building a new data frame where there's a title score and a tag score based on the tags the video has. I showed it before to you. And if you're now doing a scatter plot, you see not very good correlated. But even if you're calculating the mean, there isn't really a good correlation between title and rankings. So the same done for the tags. Nearly the same, no correlation between between tags and position for YouTube videos. So, just some slides when the Jupyter notebook doesn't work. Here in this table, I've summed up what we've just found out. There's a strong correlation between video views, video likes, and comments. There's a correlation between age, subscribers, and views, and nearly no correlation between the number of video channels and ranking, title or tag content and the video rankings. This is what we found out with just looking at about 50 queries and 50 videos each, so 2,500 videos. So this is an assumption. So how could we check if this is correct? Oh, we could do some videos, put them on some channels, watch it for 2 or 3 years and hope that our assumption is correct and the videos arrive at the position we think would fit our model. Or we could look at was too fast. A study someone else has been doing with 1 million videos, and they got nearly to the same conclusion. Comment count is strongly correlated. Number 2, the length of videos we didn't look at, but number 3, video views significantly correlated. Then 4 are the number of shares. We did not examine that, but number 5, subscriber size, somewhat correlated. Video likes strongly correlated. Just very small relationship between keywords in the tags and rankings, or the content of the title and the rankings. Just the same as we have been finding out with our little analysis that's been done in, I'd say, half a day.
But how can you use this and sell this to a client? I mean, you cannot sell views, you cannot sell or buy a big channel, you cannot buy comments at large scale, I would say. So I mean, okay, the numbers are all right, but how do you use them? If you go to a client and the client says, well, I want a top ranking video on YouTube.
Of course, it's not a good idea to buy views or to buy comments, because these are just the average numbers, the mean numbers. So if you're buying those things, I'm very sure that Google will see that, will understand this, and it will not work out for you. So buying it is not a good strategy. But you need to know this to make a strategy that pays attention to those signals. You have to have a strategy that says, oh, I want to tell my customers or my users, please write comments, or please like us on YouTube. It's a part of the strategy you're using, and you need to know this. And you need to understand, as an SEO consultant, one of the questions I hear very often. Why is this one on number 1 and we are on number 5 or 10 or 20? And then it's good to understand that, for example, in YouTube, the age plays a role. Or in Google, the number of links is very important. So I've looked at another very interesting platform, Pinterest. Pinterest is, I'd say, after Google and after YouTube, now the third largest search engine in the world. And it drives a lot of traffic to websites that use a lot of images. A study from the US says about 5% of all traffic to websites in the US is now from Pinterest. In Pinterest, you're doing some keyword search, just like in Google image search, and get something like this for Colosseum Rome. And why are you getting this? The words Rome and Colosseum are in the description, so it's easy for Pinterest to say this is a result for the query Colosseum Rome. So I've investigated it further, and there's a very interesting application in Pinterest called Pinterest Lens. It's part of the app of Pinterest, and it works like this. You have the app, you are photographing some object, it does some magic, and then it gives you images that are very similar to the one you just photographed. And if you click on this one, it says, oh, it's a optimist, so you don't know what this is, what you have just taken a photograph of, and it tells you what it is, and Pinterest wants to become a big shopping platform. And this works rather good. So I was interested if I can do the same with Python. Oops. No. There's a library called ImageHash that can determine how similar images are. And I'm reading some images from files. You see, so now you're seeing it too. So some modules again, some images from files, and you get a list of images in the folder, 2 pictures of a polar bear, one of them modified. This is the one, this is, oops, the one modified, and this is completely different image. So, and now I can calculate the hashes for all those 8 images. They look something like that. It's just an array of false and true values. And now I'm pairwise calculating the distance, the hash distance for those for those images, and printing them sorted. Value at front is the distance of both images, and you see, polar bear 1 with polar bear 1, also each image with itself is distance 0. That's not very surprising. And the different images that are most similar is polar bear 1 modified with the polar bear 1 original image. That's rather good. But if you're looking at just the polar bear 1 image to every other image, you see the people 2 image, the woman I just showed you, is better according to this image hash function than the other picture from a polar bear. So this image hash is working very good to detect very similar photos, identical images or very similar, but not to detect some objects like Pinterest Lens does. But there's an API from Microsoft Azure that can recognize images and objects in images. I've used the Colosseum picture, given it to the API, and it says it's a large building with Colosseum, so it sees there's the Colosseum in this image. Or I was using from Pixabay an image with a polar bear, and it says there are two animals. The one is an animal I don't know a lot of, and I'm not very sure about this one. It has confidence 0.5, but the second object is a polar bear, and I'm very confident with the confidence of 0.9. So this tool identifies a polar bear in this image, and it even says, it's later, it's not in the lower there, it's not in the screenshot. There's a polar bear sitting on an ice, on some ice. Rather interesting. This is the JSON in better form. There are some more things we could do experiments with. But now going from rankings to recommendations. Recommendations are very well known because of Amazon. Customers who bought this also bought that. Had a very strong influence on the e-commerce. On Netflix, I was watching Matrix, and it gives me those recommendations for similar movies. So how does this work? This is called collaborative filtering. I used the Movie Lens dataset, and that's from Kaggle, about 100,000 ratings from about 1,000 users and 1,600 movies, I think. And I try to show it again. I hope you will see it. So. But to understand what's happening, I'm using just a very small data set at the beginning with 4 users, Anne, Bert, Clyde, and Doris. Just 6 movies. And these 4 users voted for the 6 movies. And these are their votes. The number 1 is the blue line, number 2 the orange line, and so on. You see the red one did not vote for number 1, and the orange one did not vote for number 5. It's at 3.5. There's no .5 voting, so there's no dot at this point. If you have 2 such lines, we can do again some regression analysis. We get a R value of 0.46, not that bad. If we compare 1 and 3, or the blue and the green one. But if we want to compare 2 and 1, we get an error. Why? Because the user number 2 did not vote for all movies, and so we can't do linear regression here. So we have to do something else. Our first step is to merge movies and ratings into a single table. And then we can exploit a little bit further. We can see that 4 movies have been voted for by all of our users, and 2 movies just by 3. We can calculate the mean rating for the movies. Oops. And we can sort them by the mean rating. But that's not very helpful for what we try to do. We want to find similar users and similar movies. To find similar users, we're using a pivot table, have the user and all the ratings he gave for all the films, And you see user 2 did not vote for Avatar and user 4 did not vote for Star Wars. So I have to give some number for it because we have to calculate with this. And if we have this, we can calculate the pairwise cosine similarity. What's happening here is that this row is just a vector, just a simple vector, and the second row also just a simple vector. And between two vectors we can calculate a cosine similarity, and the more similar those vectors are, the larger this number is. And of course, identical vector gives number 1. So if you compare the vector from user 1 with the vector from user 1, it gets 1. And the most similar is user 1 with user 3. We've seen it in the lines. The blue one and the green one are rather similar. So this way we can find similar users. And if we now want to a recommendation for user 3, for example, we just have to find what users are most similar to user 3. In our simple model, we find user 1, and then we present to user 3 the movies user 1 has given a top voting. In this example, Star Wars, Gladiator, Finding Nemo. So, but it's more interesting to do this with the larger data set, about 1,000 users. In this data set, there's some more information. There's age, gender, and something like that. We don't use. Here we've got 1,700 movies, Toy Story, GoldenEye, etc. It's a rather old data set. And the ratings for all those movies and those users, looking something like this. Doing the same again, ratings and movies merged to a single data frame. Pivot table for the users. And so we can calculate for all the 943 users what users are similar, and we can provide them the most similar, the best movies for them. But what we want to find now is movies that are similar to another movie. So we're just doing the same pivot table for the movies. So this is movie 1, it was Toy Story, I think. Got from user 1 a 5, from user 2 4, user 3 did not vote, user 5 4, and so on. GoldenEye, user 1 gave 3 points, user 5 3 points, user 934 4 points, and so on. And now we can do the same cosine similarity for those 943 different movies. So it's not very easy to understand. So I've written a simple function where you can pass a movie index and it shows you the most similar movies. The first one I want to try out was movie with index 1 was GoldenEye. And of course the best match for GoldenEye is GoldenEye, but then there's Under Siege, I think with Steven Seagal, Top Gun, True Lies, all the blockbusters from the early 90s. I think it's not that bad as a recommendation. Now looking at Casablanca. Best recommendations for Casablanca are Citizen Kane, Wizard of Oz, Maltese Falcon, all some blockbusters from the 40s. I think very similar would fit good for a recommendation system. And a third one for Weddings and a Funeral. Harry Met Sally, Back to the Future, Forrest Gump, all those a little bit more romantic movies also from the 90s. So I think just with just with 1,000 users and 100,000 votes, we get rather good recommendations that can be used in systems. And this is what Netflix is doing, this is what YouTube is doing, Amazon, etc. Oops. Yeah, so I'm at the end. I hope it was a little bit interesting for you, and I'm very happy to answer your questions. Thank you very much.